Okay, welcome back. Let's take a look at another typical ideal projectile motion problem. Okay, so let's say we've got something, maybe we're playing baseball, we've hit a ball with some significant speed, 40 meters per second, that's around 90 miles an hour, and about 35 degrees above the horizontal, and we want to know well, what's its maximum height would be a cool thing to know. What's its horizontal range if it lands or is caught from the same height that it was launched? So I'm saying here a specification for our problem is that the change in y position overall is 0. Not for the maximum height, but for the overall problem. And how long is it in the air? What's our time of flight? So, if we take a problem like this, and we're given vector quantities, after we've written our known information here, one of the first things we want to do with our vector quantities is to break them down into components. Now, before that, we want to pick a coordinate system that works well for us. With ideal projectile motion, that's typically going to be up, vertical is positive up, and horizontal is positive x, vertical is positive y, and because that lets it be so that our acceleration is simple, and these equations hold true. Let me erase some of these holdovers from the previous question. Okay, so first thing we want to do after we've established what type of problem it is and what is our preferred coordinate system is we want to break down any of our vectors into components that align with that coordinate system. So we want to know what is the x component here. That's going to be v naught cos theta, and what is, I got that written y0, the y component of the original velocity as well. So, what are they? That's 40 cosine 35, which did not pick the, I have memorized this trig value answers here, so 35 cos 40, that's going to be, I'm going to take 3 significant digits for this one to play with, 32.8 meters per second. And then the y original, give us a little space here. That's going to be 40 sine 35, which is 22.9 meters per second. Okay, so those are our components. Now that we have those, we can play ball. So now we know how we've got information that can connect to the things we want to know. We want to know delta x, we want to know delta t. To go along with this delta y, and we'll get to the max height in a moment. So delta x we don't know, delta t we don't know. We know the original component of the y velocity. We do not know the final component of the y velocity. And for our overall flight, we do not know the change in height. So this gives us a question where this equation has a single unknown. It's one of the ones we're looking for. So let's work with that. Okay, so we do this. Delta y is v0y delta t minus, compact this a little, minus g over 2 delta t squared. And for this problem, I've given us a special case, which you often see in introductory physics courses, where the starting and ending height for your flight is the same. And so that makes this go to 0. And that makes for some mathematical convenience. Because we see in each of these terms, there are time variables. Now they're just playing algebra tricks here. So we can factor out a time. And we get delta t times this quantity in parentheses equals 0, which we remember from algebra means that either delta t is 0 or v0y minus g delta t over 2 is 0. Well, this is what we call the trivial solution. This is, oh yes, we're at 0 height when we were at 0 time. That's just stating the initial conditions of the problem. So this is the one we're interested in. And we'll go ahead and do the algebra on that one. We got, let me bring that over here. That's v0y equals g delta t over 2. So delta t is 2 v0y over g. So if you're looking for your overall flight and you're catching it the same spot it was launched from, it's landing the same height it was launched from, there's your time. So that's 2 times 22.9 over 9.81. And that is going to be about 4.5 seconds. Let's find out. 2 times 22.9. 9.8, more than 4.5. 4.67 seconds. I will call that 4.7 seconds. I'll put that up here. Delta t equals 4.7 seconds. It's 4.67. And I rounded it. Okay, so that's our time of flight. Now that we have time of flight, we can find the horizontal position. We needed to know that time in order to get the horizontal position. It's the only thing connecting us to the rest of the problem. So let's go do that. I will give us some working space here. So delta x is vx delta t. That was 32.8 meters per second times 4.67 seconds. Actually, I left the full number in my calculator still, so that's about 153, I'll call it 150 meters, which is pretty far. So pushing 500 feet, pretty good hit. So there's our horizontal range. I'll go ahead and put that up here as well. And now we can look at y max. So we remember that when a thing reaches its maximum height, it's got to turn around to go back down. And so that means that the velocity in the up direction has to be 0. Our y velocity will have to be 0 at this point. So, Vy at the max height is 0. And if we know that, then we're looking at different conditions. We're not looking at the end of the whole flight. We're looking at the spot where we have 0 y velocity. And in that case, we don't know our delta y. So this equation here has one unknown, the delta y. We get to go Vy final squared minus Vy original squared. It's minus 2g delta y. And it's 0 at the turnaround spot. And so delta y then gets to equal Vy 0 squared over 2g. So 22.9 squared over about 19.6. Let me be explicit there. That was 2 times 9.8. And so that yields about 27 meters, 26.8 meters. Okay, and so that's it. Now, we've got enough information that if we want to, we could work through the problem again and find the final velocity. But we know from experience with one-dimensional motion that the velocity in the y direction is going to be the same size as going down as it was up. We can see this in this equation over here. For the overall flight, when delta y was 0, this that makes this whole side turn to 0, and so we're left with we'd be left in that case with Vy final squared equals Vy original squared. And so Vy final equals plus minus Vy original. Well, it's going down, so you know it's minus. If we know that it's the same size as before, then it's just the same triangle, except instead of aimed at a 35-degree angle up, it's at a 35-degree angle below the horizon. So we could figure it out that way. We also could do this and find the position or the velocity at any given point in time for that flight by plugging in the times into these equations. So that'll be that for this question.